Welcome back. In this lecture, we will talk about radiation shields. Okay, so if you look at this diagram over here, this is plate number 1 and this is plate number 2. And both of them are parallel to each other and they are considered as infinitely long plates. And we assume that their areas are equal, A1 equal to A2 equal to A. So there is no change or difference in the area. They are infinitely long parallel plates, and so we assume that the area is constant. The other important parameter here is, for the time being, imagine that there is no radiation shield over here. There is only a radiative heat transfer between the plates 1 and 2. So since the plates 1 and 2 are parallel to each other, whatever radiation is going to start from plate number 1, that is going to fall at plate number 2. And what is going to uh, be emitted from the surface 2, that is going to fall on plate number 1. So your shape factor, the self shape factor F11 and F22, these two are equal to 0. Okay, and that leaves F12 and F21, and both of them are equal to 1. Okay, and you remember the shape factor algebra, there are two surfaces here. So F11 plus F12, that is supposed to be equal to 1. And since this guy is equal to 0, so that makes F12 equal to 1. So is the case with F21 as well. Okay, so in any radiative heat transfer, say for example, the heat is now exchanged between the surfaces 1 and 2. So Q12, according to whatever we have learned before, so this is going to be A times sigma T1 power 4 minus T2 to the power 4, assuming our surface temperature T1 is greater than T2. Okay, divided by the thermal resistance. What are the thermal resistances that we are having? Okay, the first one is with reference to the surface resistance pertaining to plate number 1. So surface resistance pertaining to plate number 1 is 1 minus epsilon 1 by A1 epsilon 1. The second one is going to be, the second one is going to be 1 by A1 F12. And this is the space resistance. And we know that the space resistance is because of the geometrical parameters of the plate and the distance that separates them. Okay, so the dimension of the plate and the distance that separates them, that contributes to the space resistance. And the third one is the surface resistance offered by surface number 2. And that is given by 1 minus epsilon 2 divided by A2 epsilon 2. And what we have seen here is F12 is 1. And we have assumed that A1 and A2 is equal to the area A. So if this particular thing is rewritten, this equation is rewritten, this becomes A times sigma T1 power 4 minus T2 to the power 4 whole divided by 1 minus epsilon 1 by epsilon 1 plus 1 by F12 plus 1 minus epsilon 2 by epsilon 2 into area A1 by A2. Okay, so now A1 and A2 is going to be the same. A1 and A2 are same, so I can cancel this. Okay, and your F12 is equal to 1. So that leaves this term as 1. And this 1 minus epsilon 1 by epsilon 1, that can be written as 1 by epsilon 1 minus epsilon 1 by epsilon 1, which is minus 1. Okay, so what we get here is A times sigma T1 power 4 minus T2 to the power 4 whole divided by 1 by epsilon 1 minus epsilon 1 by epsilon 1, that is minus 1. Then you already have a plus 1. Then plus 1 by epsilon 2 minus 1. That is epsilon 2 by epsilon 2 with a minus sign before it. So this minus 1 and plus 1 would get cancelled. And what you have here is A times sigma T1 power 4 minus T2 to the power 4 whole divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is the general expression that you are going to have. So let me circle it with another color. So this expression is what you are going to have for any radiation heat exchange between two parallel plates where your shape factor becomes equal to 1. Okay, and where the areas are same. Okay, so this is applicable for any two infinitely long parallel plates. Now, so this is when you have heat exchange between two long parallel plates. So now if we introduce a radiation shield between these two plates with emissivity epsilon 3, some emissivity epsilon 3, what happens? So let's look at that. So which means now the radiation that is going to start from 1, that is going to fall at 3. It's not going to reach 2 directly. Okay. And so whatever heat energy gets accumulated over here through the radiation heat transfer, that is going to be emitted from surface 3 to surface 2. So that is what is mentioned over here. So your Q13, whatever heat energy that is emitted from 1 and that reaches 3, only that can be transferred from 3 to 2. So when there is no other heat loss, the heat exchange from 1 to 3 is going to be equal to the heat exchange from 3 to 2. Okay. So this is a very, very important criteria, which is essential for deriving what we are going to do right now. Okay. So now when this radiation shield is added, so your Q13 is going to be equal to Q12. So now my expression for Q13, that is going to be equal to A times sigma T1 power 4 minus T3 power 4 whole divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1. Okay, this is the expression that we have got for Q13, and the expression for Q32 is going to be A times sigma T3 power 4 minus T2 power 4 whole divided by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay, so this is what we got here. And the expression tells us, or the condition tells us that Q13 is supposed to be equal to Q32. So when you write the expression A sigma T1 power 4 minus T3 power 4 whole divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1, this is going to be equal to A times sigma T3 power 4 minus T2 power 4 whole divided by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. And this A sigma are common in both the cases, so that can be cancelled out. So whatever remaining expression that you have got, so now you will be able to find the temperature T3 of the radiation shield from this particular expression. Okay. And one more question that may be asked in radiation shield is this: what is the percentage reduction in heat transfer when you use a radiation shield? So your Q12 is the heat transfer or heat exchange without radiation shields. And Q13 is going to be the heat exchange with radiation shield. So the percentage reduction in heat transfer, so that is going to be equal to Q12 minus Q13 divided by Q12 multiplied by 100. Okay. So the concept is very simple. So the advantage of using the radiation shield is, see, there is no heat loss. Okay. Without eliminating heat exchange, we are able to reduce the heat exchange between two surfaces. Okay. So that is the advantages of using a radiation shield. And by using the radiation shield, we will be able to reduce the amount of heat exchange between two surfaces considerably. Okay. So now let's look at a couple of examples and then we shall wind up this session. Okay. So now what is given in this problem is calculate the net radiate heat exchange per meter squared area for two large parallel plates at temperatures 700 and 300 Kelvin respectively. So you have got two plates. You have got plate number 1 and you have got plate number 2. So this is plate number 1 and 2. The temperature of plate number 1 is given as 700 Kelvin. Obviously, this is at a higher temperature. And plate number 2 is at 300 Kelvin. Okay. And epsilon 1 in this case is 0.9 because this is the hot plate and this is the cold plate for which epsilon is 0.6. And the second question is, if a polished aluminum shield is placed between these two plates. So now if you introduce a radiation shield over here with emissivity 0.4, they are asking us to find out the reduction in the heat transfer rate. Okay, so let's first find out what is the heat transfer without the radiation shield. So this guy Q12, this is going to be the heat transfer without radiation shield. That is the heat exchange between two surfaces. Okay, as per the derivation which we have done so far, so this can be written as, so it is per meter squared. So you can eliminate this area over here. It's a heat flux. So it is sigma times T1 power 4 minus T2 to the power 4 whole divided by 1 by sigma 1, sorry, epsilon 1 by 1 by epsilon 2 minus 1. So that is 5.67 into 10 to the power minus 8 times 700 to the power 4 minus 300 to the power 4 whole divided by 1 by 0.9 plus 1 by 0.6 minus 1. And we've used the calculator to calculate this. So it is 700 to the power 4 minus 300 to the power 4 multiplied by 5.67 into 10 to the power minus 8 divided by 1 by 0.9 plus 1 by 0.6 minus 1. So it gives me 7,300 7,399.35. So this guy over here is 7,399.35 watts. So this is the heat transfer that I'm able to get without the radiation shield. So the next part of the question is, so now if you are going to introduce, a radiation shield, say I'm introducing a radiation shield over here. So if I introduce a radiation shield over here with emissivity epsilon 3 equal to 0.4. Okay, so if that is the case, then what happens? So what we know is Q13 is supposed to be equal to Q32. That is what we saw in the derivation as well, because the radiation shield is not absorbing any loss, it is just reducing the heat exchange. So it is sigma times T1 power 4 minus T3 power 4 whole divided by 1 by sigma epsilon 1 by 1 by epsilon 3 minus 1. This is going to be equal to sigma times T3 power 4 minus T2 to the power 4 whole divided by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay, so if we substitute the values, you can cancel out the sigma and sigma over here. So it is 700 to the power 4 minus T3 power 4 whole divided by 1 by 0.9 plus 1 by 0.4 minus 1. That is going to be equal to T3 power 4 minus 300 to the power 4 divided by 1 by 0.4 plus 1 by 0.6 minus 1. So now you will be able to get an expression, or you will be able to get the value of the temperature T3. So on solving this equation, you will be able to get T3 equal to 595 Kelvin. That is the value that is given in the textbook. You can cross check. Okay. But this is not we want. What we require is what is the heat transfer that has happened with the radiation shield. So what we require is sigma times T1 power 4 minus T3 power 4 whole divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1. Or you can also find the value of Q32 because Q13 is going to be equal to Q32. You can use any of these two equations and you should be getting the same answer. So 5.67 into 10 to the power minus 8 into 700 to the power 4 minus 595 to the power 4 whole divided by 1 by 0.9 plus 1 by 0.4 minus 1. So let me use the calculator and see what I get for this. So that is 700 to the power 4 minus 595 to the power 4 into 5.67 into 10 to the power minus 8 divided by 1 by 0.9 1 by 0.4 minus 1. So that gives me 2492.14. 2492.14 watts. So initially it is 7,000, almost 7,400, and it is almost 2,500. Okay. So now the difference, the reduction in the heat transfer rate. So percentage reduction in heat transfer rate is going to be equal to, and this is watt per meter square, because it is per area, isn't it? So the unit is supposed to be watt per meter squared for both the cases. So 7,399.35. 7,399.35 minus 2492.14 whole divided by 7,399.35. So that is going to be equal to so that is 66.32%. So this much amount of heat is reduced, or heat exchange is reduced when we use a radiation shield. So this is one example. The next example that we will look at is just the same problem, but just to introduce another topic to you, or another methodology of solving the problem. So determine the radiant heat flux between two large parallel plates of emissivities 0.8 and 0.5 held at temperatures 1000 and 500 Kelvin. If a thin copper plate of emissivity 0.1 is introduced. So now the question is very simple. So you have got plate number 1, and there is plate number 2, and there is another plate that is introduced, which is plate number 3. So this plate number 1 is at 1000 Kelvin. This plate number 2 is at 500 Kelvin. Epsilon 1 is 0.8 and epsilon 2 over here is 0.5 and epsilon 3 is 0.1. Okay. So now the question is, what is the heat flux between the two large parallel plates? So I am supposed to find out the value of Q12 by taking into consideration this 3 as well. Okay. So now I just want you to remember what we did in our conduction problem. Say, for example, a composite wall problem. Say you have got three layers. Say the temperature T1, T2, T3, and T4. T2 and T3 are interface temperatures. And let's say this length is L1, L2, and L3. And you have got K1, K2, and K3. And maybe you can also say area of the wall over here is A1, A2, A3. So when we want to find the net heat transfer rate, we usually say it is delta T overall divided by the total thermal resistance. So delta T overall by R thermal total. So what we had here is T1 minus T4 whole divided by, we used to write this as L1 A1 by K1 plus L2 A2 by K2 plus L3 A3 by K3. Similarly, in this case also, you want to find the net heat transfer. So this is going to be, so this guy is going to be T1 power 4 this is T1 power 4 minus T2 power 4. That is going to be the overall difference, but raised to the power 4 multiplied by sigma whole divided by the resistances that we have got. So the first resistance is going to be 1 by sigma 1, sorry, epsilon 1 plus 1 by epsilon 3 minus 1. That is the thermal resistance that we have got between 1 and 3. And the next resistance is going to be 1 by epsilon 3 plus 1 by epsilon 2 minus 1. That's it. So if you are going to substitute the values over here, then that is going to give you the answer. So 1000 power 4 minus 500 to the power 4 whole divided by 1 by 0.8 plus 1 by 0.1 minus 1 plus 1 by 0.1 plus 1 by 0.5 minus 1. So if you use the calculator for this, so that is 1000 power 4 minus 500 to the power 4 multiplied by 5.67 into 10 to the power minus 8 divided by 1 by 0.8 plus 1 by 0.1 minus 1 plus 1 by 0.1 plus 1 by 0.5 minus 1. So that gives us 5196.98 watt per meter square. So this is the answer that I get by using the calculator, but I would request you to check this value. Okay. So that's it for today.